In this section, we look briefly at compressed sensing. This is a very well studied area and a celebrated topic. It has received much attention in the past. It's already been the subject of many tutorials. As such, our goal is not to give a comprehensive overview of compressed sensing. Far from that. Rather, we'll try to get just enough information to be able to draw intuition from the many successes in the field. More specifically, we want to understand the problem formulation, introduce some notation that we'll use later, and review well-known approaches to compressed sensing. Our treatment is heavily influenced by the notion of compressed sensing put forth by Donahoe, Candace, Tao, and Romberg around 2006. Still, it's worth mentioning that many other scholars have contributed to this rich area. We begin our treatment with an underdetermined system of linear equations that's characterized by a sensing matrix phi, a sparse vector S, and an observation vector Y. The matrix is something that we can design in the sense that we have some control over its elements. The columns of phi can be thought of as atoms, which, when aggregated, form a dictionary. Vector S is sparse in the sense that it admits a sparse representation with respect to the columns of phi. In other words, we know that S only has a few non-zero entries. A common way to state this property is to say that S has a small L0 pseudonorm. In this context, observation Y is obtained as the product of matrix phi times vector S. This yields the canonical compressed sensing equation Y is equal to phi times S. In this cartoonish example, sparse vector S has 4 non-zero entries, each with distinct values. We can fold the vector over matrix phi, where each vector entry multiplies a column. After this operation, we are left with 4 columns, each of which is a scaled version of an original atom in the dictionary. When we add them up, we get observation Y. This should be all very straightforward to people familiar with compressed sensing. Of course, a proverbial goal at this point is to recover vector S from observation Y. In this sense, this task is an inverse problem. Since the linear system is underdetermined, and assuming that matrix phi is full rank, we know that there are an infinite number of solutions to this system of linear equations. However, we're interested in recovering not an arbitrary solution, but the original sparse vector S. In fact, I should say that we're not interested in a specific instance of a compressed sensing problem. What we want is to review conditions that will make it possible to recover sparse vector S with high probability. To make this more precise, it's common to examine the behavior of large or asymptotic systems. And to do so, we add up some of the definitions that were introduced by Donahoe, Maleki, and Montanari in a 2009 article entitled Message Passing Algorithms for Compressed Sensing. This framework is especially meaningful because it sets up the quantities we need to talk about design strategies for super large systems. And that's what we're ultimately interested in. We focus primarily on 3 quantities. The first one is the undersampling fraction, which we denote by delta. It is equal to the number of rows in sensing matrix phi divided by the number of columns. Here we use lowercase n to denote the number of samples, and we use capital N to represent the number of columns. Since this is an underdetermined system of linear equations, the width of phi is always greater than or equal to its height, and as such, delta is a number between 0 and 1. In the asymptotic regime, the height and the width of phi become large, with their ratio converging to constant delta. We know that if we admit more samples, then the problem becomes easier because we can always disregard observations. The second quantity we are interested in is a measure of sparsity, which we denote by rho. This quantity is equal to the number of non-zero entries in sparse vector S over the total number of rows in sensing matrix phi. If the number of samples is less than the sparsity of S, which we denote by K, then there will be an infinite number of possible solutions within the support of S. This can be seen through the fact that even when we restrict sensing matrix phi to the columns or atoms attached with the non-zero entries in S, the linear system remains underdetermined. Clearly, under such circumstances, exact reconstruction is impossible and the problem becomes uninteresting. As such, we'll focus on situations where the measure of sparsity rho lies between 0 and 1. Again, this is an asymptotic notion. So what we really mean is that in considering large systems, we let k and n go to infinity with their ratio converging to a constant, and we call this constant rho. One of the celebrated results in compressed sensing is that for large systems and under certain conditions, such as the restricted isometry property, exact reconstruction is possible with high probability, provided that the number of samples is at least on the order of k log n. And that's pretty amazing. The third quantity that we look at is simply the width of the sensing matrix, or the number of columns. This is an unusual quantity to look at in the theory of compressed sensing because it doesn't play a fundamental role in determining what's possible. In fact, when one considers an asymptotic regime, the width of the sensing matrix grows to infinity. Nevertheless, when we look at practical algorithms, the number of columns becomes crucial. If it is reasonably small, say less than 10,000 columns, then one can use very sophisticated methods. However, beyond a certain point, one often has to resort to simpler first-order methods. The design of the matrix also becomes very important because some constructions invite fast techniques such as the fast Fourier transform or the fast Walsh-Hadamard transform. Still, beyond a point, one needs to think of alternate algorithmic constructions. Established CS solvers, even the simplest ones, will simply not work on a standard computer. For instance, what should one do if they are faced with a matrix that has way more than 1,000,000 columns? Designing ways to address these situations is where we're going. But before we get there, we review two important strategies to solve compressed sensing problems as building blocks. The first approach we review is the principle of basis pursuit for decomposing a signal into an optimal number of atoms. This was proposed by Donohoe and his collaborators in the mid-1990s, and it is closely related to the least absolute shrinkage and selection operator, or LASSO, which was introduced by Tibshirani in 1996. Essentially, researchers realized that using the L1 norm as a regularizer within an optimization objective leads to a convex problem that often produces a sparse solution. The sparsity-inducing character of the L1 norm is key in identifying the right vector S, while the fact that this is a convex optimization problem suggests that it is possible to derive low-complexity solvers. There have been many contributions on applying this philosophy to various settings. For noiseless problems, basis pursuit can be transformed into a linear program. This can be solved using standard techniques such as the simplex algorithm or enter-your point methods. In the presence of noise, the problem becomes a quadratic program. And in general, tools such as LP, the iterative self-thresholding algorithm, with or without momentum, non-negative least squares, or non-negative least absolute deviations can all play a role in getting a sparse solution to such an optimization problem. This is not a comprehensive list. The literature on this topic is vast. It suffices to say that if a compressed sensing problem is of a reasonable size, and if it is well-conditioned, then there are off-the-shelf API-out solvers that can be leveraged to rapidly get a solution. We will keep this fact in mind as we move forward. One solution path that we examine more closely for compressed sensing problems is the approximate message passing algorithm, or AMP. This algorithm features 3 steps. The first step is the computation of a residual through synthesis. Basically, residual z is equal to the original observation y minus phi times your current guess about what vector s should be. The second step is rooted in analysis, and it involves computing an effective observation. Here we have phi transpose times your residual z plus your current guess about what vector s should be. The last step is denoising. This is an opportunity to improve your current estimate of what vector s should be by taking into consideration the effective observation as well as the known structure of the signal. For instance, when s is known to be sparse, a common denoising function is the soft thresholding operator shown here. So far, our explanation of AMP is very much aligned with iterative soft thresholding. The last component of the AMP algorithm is the introduction of a correction term called the Unsagger term that essentially prevents self-interference during iterations. One way to motivate the presence of the Unsagger term is to draw an analogy between AMP and loopy belief propagation. Alternatively, one can use a more mathematical approach with a Taylor series expansion to determine the form of the Unsagger correction. Here again, there have been many excellent tutorials on this particular topic, and as such, we spend little time on the subject. Yet it is pertinent to say that for our purposes, AMP is a low complexity solver for large compressed sensing problems, and it is much more general than what's shown on this particular slide. Under some Gaussian assumption and regularity conditions, the AMP framework is remarkably mathematically tractable. The last notion we want to look at in this section is the sparsity undersampling trade-off. The figure shown on this slide comes from the same 2009 article by Donahoe, Maliki, and Montanari that we pointed to earlier on. We focus on two types of problems. The curve in red corresponds to a sparse problem where non-zero entries are known to be positive, whereas for the blue curve, the non-zero entries can be anything. On the x-axis, we have the undersampling fraction, delta, which is the height of the sensing matrix over its width. On the y-axis, we have the measure of sparsity, rho, which is the ratio of the number of non-zero entries in S over the height of the sensing matrix. Asymptotically, as the height, the width, and the number of non-zero entries go to infinity with proper ratios, a phase transition phenomenon occurs. When the operating point is below the line, exact reconstruction happens with vanishing probability of error. However, if we are operating over the line, or above the line I should say, reconstruction fails. The two versions of this sparse recovery problem produce different boundaries, with the easier problem, the one with non-negative entries, having a larger region where exact reconstruction is possible. More importantly, we know that such phase transitions are very frequent when using AMP. At this time, we conclude our brief overview of compressed sensing. Hopefully, we've accomplished our goals. We have a common understanding of compressed sensing, of what it offers and of its limitations. We have a notation that we can use in the remainder of this series. We have two types of solvers, the basis pursuit lasso type approach and the more recent AMP algorithm. We also have an understanding of phase transition phenomenon in solving large compressed sensing problems. We end this section with a few key references and pointers for the material we've covered.